ఈ జాయిన్ అయిపోతున్నా అయిపోయి
Meeting ID pass.
Hello.
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 Is that clear?
Hello, all good evening. We will start in 5 minutes. Hello, all. Good evening, everyone. So, hope I'm audible to all. So, it's our pleasure to have each and every one of you present at this session. And I extend a warm welcome to all of you, including my esteemed colleagues, respected faculty, and the Innovation Hub at IHub-Data, Hyderabad. I'm so delighted to see you all here. And now I'd like to introduce Dr. Mona Lisa ma'am. Dr. Mona Lisa ma'am holds the Master of Science degree from Jadavpur University and completed her PhD at IISc Bangalore, specializing in high energy physics, and following she pursued her postdoctoral research in Switzerland. Currently, she is working in a teaching role at IIIT Hyderabad, specializing in artificial intelligence and also working as a subject matter expert with experience in machine learning, deep learning, and cloud computing. So I would like to welcome Dr. Mona Lisa ma'am once again and guiding the session focused on this machine learning program. Over to you, ma'am.
Thank you, Midhuna, for this warm welcome. So welcome everyone to today's session. And so let me see, and then we'll get started. Yeah. I hope my screen is visible to everyone.
Yes, ma'am. Visible.
Okay, great. Okay. Okay, so let's start with today's session. Now, before we start with the session, there are a couple of things which I'd like to share with you. First is during the session, say after every 15 to 20 minutes, we will have a break where we can discuss if you have any queries or if some part is not clear to you. So I would request you to save your questions till we are on that break. And if there is some concept which I am teaching and it's not clear to you, then you can stop me at that time, and then I can repeat that concept again. Okay. So this is something which I would like to put before you. And as you already know that today being the first session, today we will be learning about the basic concepts of linear algebra. Now, linear algebra, this concept have heard a lot, and as you can clearly understand from this term that it's composed of two parts, that is linear and algebra. So what is algebra? So can anyone tell me here, like, what do you understand by algebra? Anyone? Okay, so probably I can have a look here. Chat, yes. Algebra, which means joining broken spaces. Okay, good. Anyone else wants to add to what Omar has written here? Okay. So let's see. So algebra, as we have all done in our school days, what exactly we were doing in algebra? We were saying that it is a branch of science where you are actually studying some mathematical symbols, and there are some rules for manipulating these symbols. Say we have some equations like, say I am writing some equations, say like 5x equal to 25. So what I'm trying to do is that here my term is that I have to find the value of x such that when it is multiplied by 5, it is giving me some value of 25. Now this is like, we also have the term linear. So linear, as we will go through this session, you will get to know that linear is something which you are referring to as very simple equations. Okay. So why exactly are we studying this thing? This is what I will be motivating you in today's session. The first part of this series will be, what I will do is that I will try to motivate you why exactly we are studying linear algebra in this course of machine learning. Okay. So let us first get started with that. So first I will be starting with a very simple example from machine learning. So machine learning, as you can say, that this is an algorithm. algorithm, which is actually trying to learn something from your data. And then depending on that, it is giving you some predictions. So this is like in simple term, if you want to define machine learning. So you have some data, you are designing an algorithm, it is learning from your data, and then it is giving you some predictions. Okay. Now let's start with a very simple example. The example is like, let's say I want to predict the price of the house. So there is a real estate agent and he wants to sell the house, but he has no idea like what should be the price of the house, at what price he should be selling the house. Yes, any questions, anyone? If no questions, then I would request you to please mute yourself. Okay. Okay. Now the thing is, the real estate agent, he has to determine like at what price he should be selling the house so that the price is not too low. Otherwise, he will be having a loss. Or if he sets a very high price, there will be no buyers. So how exactly will he proceed with the problem? Okay. So in order to do this in the context of machine learning, as you will see during the course, first, what we have to do, we have to go back to the data. Okay. So therefore, my first step will be that I have to go back to my past data. To my past data means I have to go back to say last 5 years, and I have to see how the houses were sold in the past 5 years. Okay. Now, if any house is sold, obviously there are some parameters on which the price of the house will be based. Okay. So when you are like going to rent an apartment or you are going to buy an apartment, obviously there are some parameters which you are looking. Depending on that, you will be deciding whether you should be paying more or you should be paying less for that particular apartment. Okay. So can anyone here tell me like what are the parameters you should be looking at? Anyone here? Yes. Size, carpet area, good. So these are neighborhood, good. Location, yes.
How old
Features
is
of
this
the house,
house?
yes. Very good. So you can see there are several features here which you will be looking into, which can determine what should be the price of your house. Okay. Now, what are the different features? 1 minute. Yes, the feature can be the area of the house, which is the carpet area of the house. The feature can be how old is your house, whether it is a new apartment or it is an old apartment. It can be the number of bedrooms in the house, the number of bathrooms, whether it is located in the near the main road or whether it is located in some desolate area, whether it has a parking facility or not, how many stories are there, and then you have several other features. So you can see that we have several features which will be determining, and what it will determine, the final thing, which is the price of the house. So I cannot see this. Let me, yes. Yes. So it is determining the price of the house. Now, once you establish that these are the features which are determining your price, then you start collecting your samples. That is from the last, say, 5 years or 10 years, you start collecting the data. So let's say I have collected here, say, n samples. Okay. So n data has been collected by me. And for each of these n samples, I am having these values of area, age, bedroom. So all these values are there. I am plugging in these values. All these values are there. And I also know at what price these houses were sold, because this is something from the past. So I also have the respective prices of the house. Now, once we have this, now you can see, now your picture is becoming clearer to you. What I have to do now, simple relation between this price of the house, these are the y's, and the features. Okay. So that is, I have to find a function which will relate these features. The features are denoted by x. So x up to m in samples here. So that's why I'm writing f of x n1 to nm and that is related to the price of the house. So our now main problem is to solve this f. So once we find this function f, we can then start predicting the price of the house. So that is what we have done. Now, what will be this form of f? That is the main question which comes now. Like, what exactly should be the structure that will determine this? There will be different ways these structures can be defined. Somebody can say that let's start with the simplest assumption. What is the simplest assumption? That this f will be some linear combination of these values. So these are my features. So it will be some linear combination. What is that? That there will be some values like A1, A2, A3, and depending on this value of A1, A2, A3, the price of the house will be determined. So this is your simple linear combination of features. And there will be some people among you who will say that, no, it cannot be that this simple. Probably there is a complex relationship between here, that probably these features, they are mixed in some complicated way, and that is determining the price of the house. So here actually you can see a simple thing. When we are going with these simple linear combinations, we actually refer, okay? So when we will be seeing in the future, when you will be dealing with different machine learning techniques, such as, linear regression or something like that, that is known as your, what you are doing here is that in this type of learning, you are taking some simple combination of the features and then you are doing your calculations. But when you go to deep learning, neural network, which we have heard, what happens there is that your algorithm is trying to understand some complex relationship between these features, like how the age of the house, the location of the house, the area of the house, they are determining the price in a very simple way, or there is some complex, intervening relationship there. So that is what, when you go for complex relationships, we go with deep learning. And when we have very simple relationships, we are usually really going with machine learning. That is your regression, classification algorithms, okay? Now, in this lecture, we will be concentrating on this simple linear combination of features. So this is something which we will be discussing today. Linear combination, because you can see everything is linear, like no power is there, everybody is to the power of 1. Okay, all the features are power of 1. Now that we know about this, so let us proceed ahead. So this is what we are getting, that all our prices are related to all the features by some simple linear equations. So our main goal will now be to find these variables A1 to AM. That's all. So if you find these simple variables A1 to AM, then what will happen in the future, like if in the future there is a new house in the market, then you can just plug in the area of the house, the number of bedrooms in the house and other things here, and you can actually predict what should be the estimated price of the house depending on the past data. So that is our main goal now. We have to find the variables A1 to AM, which is best explaining the relationship between my X and between the Y, that is the price of the house. So if I write that in a very compact notation, what I will do, these all X1 to XNM, I am writing as capital X. All these A's I am writing as small a, and all the price I am writing as capital Y. Okay, so this is how I am writing this in a compact form. So what is my equation standing now? My equation is now standing as XA equal to Y. So this complicated where I was writing all things differently, like as you can see here I was writing everything in a separate way. So all these things were written separately. If I write that in a compact notation, I am getting this simple equation. So this is what I want to tell you here is that you saw we started with a simple example related to machine learning, and we found that it actually boils down to this simple equation which you have to solve. So where XA equal to Y. So what is XA and Y here? So X, as you can see, it is a matrix. Okay. So this is what we will try, we will learn afterwards, what is matrix, what is vector. But for the time being, you take from me, X is a matrix here, A is a vector, and Y is a vector. So what exactly is happening here? We are applying a matrix to a vector and we are transforming it into another vector. Okay. So there is a, not now. So there is a vector A. Okay. So you have a vector A. On this vector, I am applying a matrix. Okay. So this matrix, when I'm applying to this vector, I am getting another vector Y. So this form of relation, it is known as a linear transformation or linear equation. Why? Because you are transforming the vector A to vector Y. So every like simple, what we can say, like every in machine learning, simple examples or simple problems you will be dealing, that will basically boil down to this simple formula where you have a matrix space and you have to find the vector on which, if this matrix space is applied, it will be transformed into your final result. Okay, so that is why it is known as a linear transformation. Linear transformation, you might have experienced this in your previous studies, like in the form of rotation matrix, where you have a vector, you are performing a rotation, it rotates in the another. So this is one way. Now there is another way this equation can take, which we will see in the future classes. That is, when you are applying your matrix to your vector, the vector is getting scaled. Lambda is a scalar. That means if your vector was on the form like 1 and 2, okay, after applying the matrix, probably it is becoming double. So it is becoming 2, but the vector is remaining the same. It is not changing completely into another form. Okay, so this is just getting scaled. So when I'm saying this is getting scaled, this is actually will give you to the concept of eigenvalues and eigenvectors. This concept we will discuss in our later part of our classes, not today, probably after 1 or 2 weeks. So this is another way this type of equations can do. Other way what we can do is that when a matrix is applied to a vector, this transformation, it reduces it to 0. That is, it annihilates that vector, it kills that vector. So you can see that there are like these 3 type of relationships, like broad way I can say, where on applying a transformation to a vector, you can change it to another vector. That is your linear transformation. Or you can apply a transformation to a vector and you can scale that vector. That will give rise to your eigenvalue equations. Or you can apply a transformation to a vector and change it to a null vector. That is a 0. So these are the 3 type of equations which we will be encountering during our course on machine learning. And these equations are nothing but they can be solved with the concept of linear algebra, which actually tells you how you can deal with matrices and vectors and scalars using some simple linear equations. Okay, so I would like to stop now here and take your questions. Any queries or anything you have, we can discuss now. I hope till now it's clear to you why exactly in machine learning we need to have some knowledge of. Yes, any questions you can write in the chat also. Okay, actually 3 of this will be used in machine learning. Today we will we just saw one example of this first one which we saw, and the next we will be using in our next sessions when we will deal with dimensionality reduction. This we will be using in our linear regression. Okay, then why are this method? Actually Okay, sure. So the thing is that, as you saw, so when I went to this example of prediction, so when you are predicting something, these predictions can be anything. So here I am giving you an example of, it can be like, some recommendation systems, it can be like some classification problems. So whenever in machine learning, what happens is that you are training your algorithm on something and then you are getting your result. So this simple concept, so you are training on some features. So these are the features. So this is the data you are training, and then you are getting, and this is the result which you want. Now, in order to find the relationship between this, we saw that there has to be some function which is relating these features with your final price, which you need to predict. It can be anything in your machine learning algorithm, which you are like your output, which you want to predict. Now, this simple function, it can take any form. As I told you, the function, it can take any form. It can take the form of a linear combination, or it can be a complex one. So complex one, we are not dealing with now. We are dealing with some simple linear combination. So when we are dealing with this simple linear combination, we are seeing that it has to be of this form. The form is like where you have a matrix and this is a vector. So this A1, A2, A3, these are some vectors. So the matrix is applied on a vector and you are getting the result in the form of another vector. So this is a sort of a like simple equations which we can actually solve with the help of linear algebra. Now, when I'm saying this matrix is applied on a vector, this is known as a transformation, because I have one thing, I am changing it into another thing. So this is also a vector, this is also a vector. But you can see that forms are different. So I'm changing one vector to another vector. That is why it is known as a transformation equation. And this transformation is linear because you can see there are no powers of higher powers here. So that's why it's known as a linear transformation. Now, this transformation can happen in different ways. It can change a vector to a vector. It can change a vector to 0, or it can just scale a vector. So these are the different type of transformations which can happen, and these different type of transformations we will be encountering in our course in the future in different ways, which we will see as we go in the future. You will see. Okay, is this clear now? Any questions? Yes, we will use linear algebra for dimensionality reduction. So you see this equation xa equal to lambda a. This is the main equation which we will be using for dimensionality reduction. But that is something which we'll discuss in other lectures. Okay. Then how can you say that a and y are vectors? Good question. I will come to this afterwards. And what does vector A represent? So vector A, as I told you here, vector A is nothing, but this is something we don't know. Okay. So here what we are seeing that in order to understand how the features are related to the price of the house, we have to define some vector here. So you can see the relation which we defined before. This is the relation. Y1 equal to A1 X1. So in order to define the relation between Y and X, we have to find A. So this is what our main motive will be, how your machine learning algorithm is finding these A's. Okay. So that is A is the variable which is actually defining the relationship between Y and X. Okay. Yes. Yes. Any other questions, students? Okay. So I hope now you all are convinced with me that we have some, so let me just go to the next slides now. So you all are now convinced that these are the basic relations which we will be encountering in our machine learning classes in the future, where we have some matrix which is applied to a vector and then we are getting another vector, or you can apply it to a vector and then you are just scaling that vector, or you are giving it to 0. Now the question, one of your question was how you can know that X is a matrix, A is a vector, Y is a vector. Why exactly are we telling them vector and why these are matrices? And this is what we will be now discussing in the next part of the session. Okay. Any questions? No. For the time being, you don't need to study group theory here. And I don't think group theory is required that much. If you have some basic knowledge of like what is group, it's okay. No need to go into details. Okay. And lambda here is a scalar, like how much the vector is scaled. Here you can say, like, if I'm applying it to this number is getting double, or it is reducing, or it is getting 5 times, 6 times. So that is lambda. Okay. It is telling you how much the scaling is happening. It is remaining as it is, or if lambda is 1, like the vector will remain as it is. If it is become lambda is 2, that means it is, getting double its size, or it is getting half of its size. Depending on the lambda, you can understand how much the extension or stretching or is happening here. Okay. Any other questions? Okay. So now let's move to the next part. Now we will try to understand what is vector, what is matrix, what is scalar. So let us try to understand these things, and then again we'll come back to this slide. And then we will see if the concept is clear to you. So let's start with our first part. First, we will try to understand what is vector. Okay. Again, I would like your help here. Can anyone tell me what is a vector? You all have encountered it before. Okay, Sandeep, you want to recap? Okay, I will give you. In the meantime, can anybody write here vector, magnitude plus direction, single dimensional values? Okay, good. Regarding the recap, so what we did was we started with a simple machine learning example where we saw that in any sort of simple algorithms, if you want to predict some output, you have to know which has given in a data, they are related to in the past data. In order to understand that relation, you have to write the equation in the form of simple xa equal to y. Okay. Now, when I was telling about those simple relation, there I introduced you to the concept of matrix, vectors, and scalars. Now today we will try to understand what is a vector, what is a matrix, and what is a scalar. This is just a simple recap session for you all. Okay, so let's start. So as you all said, like vectors, what exactly is a vector? Vectors are nothing but which has both magnitude and direction. So this is what many of you wrote here in the chat box. Now what happens is that in very simple way, I can say that vectors are simple representations with directions. So these are some things for which in order to define those, you need to give two values. That means, say, if I tell you that today I went for a walk and I I walked for 5 kilometers. So when I'm saying I walked for 5 kilometers, so I'm giving you only one value here. So this is like I walked 5 kilometers. So this is your scalar. Scalar, why? Because I'm giving you a simple number that today I walk for 5 kilometers. So you are giving only one number here. So this is known as your scalar. Okay. So scalar is nothing but a simple number. Now what will happen is that if I now tell you that today I walked 5 kilometers in the northern direction. From my house, I walked 5 kilometers in the northern direction. So what I will do here, like now I have to write it in this way. I have to give an arrow because I have to point that today I walked in the north direction and it was 5 kilometers. So this is known as your vector, because in order to define a vector, you have to give the number as well as the direction. Okay. So that is why it is written here. These are arrows pointing in space, where the length of the arrow represents the magnitude. Because if I say I walked 5 kilometers, then someone among you will say, today I walked 3 kilometers in the north direction. So what you will do? Your vector will be like this, because you walked only 3 kilometers. Okay. So that is what it is saying, that here the length of the arrow, it represents the magnitude. Magnitude is 5 and 3 here. And the direction of the arrow, it represents the direction, whether it is in the north direction or northeast, northwest, any direction. So the arrow will point in that direction. Okay. Now, how do we represent a vector? Vectors can be represented in many ways: in a geometrical notation, in algebraic notation, in our machine learning notation. So let us try to understand in different notations. So geometrically, what it is defined as an arrow and with some direction which is pointing in the space. So how do we define the direction? The direction is defined by some reference frame. So here I am saying that this is my reference frame. So where I have say X and Y. So these are my X and Y. So this is the reference frame here. And I'm saying here this vector V, it is defined as some angle with this reference frame with X. So I am taking that X is my frame of reference and I am defining the vector is at some angle to this X. Okay. So this is the way in which a vector is geometrically defined. Okay. Now, what exactly is the physical significance here in the context of, say, machine learning? Now, suppose in this class, I want to say that I want to do a survey and I want to find the, let's say, the height and the weight of all the students in this class. Okay. So what I will do, I will collect the height and the weight, and these are only two features here, two variables here. Okay. Height is along my X direction and weight is along my Y direction. Okay. And in machine learning, what it will do is that it will take, say, for a particular student, it will take the height and the weight. So if I write it in a general notation, in a vector notation, how we do is that we write it in a square bracket, or you write it in a round bracket. Sometimes it is square or sometimes it is round. In the notation, it differs, but both are same. Okay. What people do is that, so this vector, it is saying that the height is 175 centimeter and the weight is 64 kilo. Now in machine learning, what people do is that they write it in this form. So whenever in the future classes, when we will be dealing with vectors, we will be writing it in this form as a tuple. They are writing like 175 and 64. Okay. So what it is saying here is that it is saying that in this two-dimensional space, so R2, 2 is because I have only two features here. So this is something which I want you all to understand. So whenever in the future we are writing, it belongs to R2, 2 here because we have only two features, two coordinates here, X and Y. If I had, say, if I'm also taking the age of the students, so it will be three-dimensional here. So if I also take the age of the student here, so it will then become R3. And what is R? R means I am only dealing with real numbers. I am not dealing with any complex numbers. If I deal with complex numbers, then it will be C. Okay. So my vector here, it is belonging to R2 space. Like all the vectors which I will be constructing here, they are of real numbers and they are of two-dimensional, like only two values are there. Okay. So this is how your vector is defined. Is this definition of vector clear to everyone? Okay, great. Abelian group is something which we actually don't require here, but later I will tell you about this. What is not clear, Sumit? Which part is not clear? Okay, we will see. As we go ahead, R2. Okay. 2, as you can see, I am defining 2 here because here I have only 2 coordinates, x and y. That is your height and the weight. That's why it's 2. You can see I have only two scalars to represent this vector. So I have only 2 numbers here in this particular vector representation. Now, had there been, I had also taken the age of the student, then it would have been another number, say it means say 21. So then it would have become R3. And R because I am only dealing with real numbers. Okay. So this is like, these are all real numbers. If I would have dealt with complex number, it would have become C. Okay. So this is the vector representation which I am doing. As we go ahead, it will become more and more clear to you. Now, what are the different operations which you can do with the vector? So let's quickly brush this. So suppose if I have a vector V, and if I multiply it with a scalar, okay? So when I'm multiplying a scalar, as you know, is just a number. So let us say the scalar is some number, say K. So depending on the value of K, the vector will actually, it will elongate or it will compress, depending on that. So let's say if I am multiplying my vector with 2. So what it will do, the direction will be staying the same. So it will be in the same direction as before, but it will be twice as long as V. So that is what it will become. Now say if I multiply it with another scalar, say minus 0.5. So since it is minus, so what will happen? The direction will change. If it is plus, it will be in the same direction as the original vector. If it is minus, it will instantly change. And it is saying here it is 0.5. That means the original vector will be reduced to half here. So this is the way in which your scalar multiplication happens. Now the next thing what we can do is with vector is vector addition. So we will be adding 2 vectors. Now how exactly 2 vectors are added? So let's see here. Suppose if you have a vector V and you have another vector W. Now I need to add 2 vectors. So I will show you both how you can do it geometrically and how you can do it algebraically. So geometrically what we do is that the vector sum is obtained by placing one vector and the other vector will be placed such that the tail of this vector will be near to the head of the vector. That is, it will be like this. So you can see, I have brought this W, the tail of W to the head of V. Okay, so this is known as the law of parallelogram, which you can have a look. So this is the simple way in which we do. We take the head of a vector and we then to it we add the tail of the another vector. After that, we join this thing and that is the sum of the 2 vectors. Okay. So in simple way, you can think of this as, suppose this is my coordinate system. So this is your X and Y. And what happens is that I have a vector here, a small one. And this is the value here, say 3 and 2. So what is 3 and 2? 3, 2 means on its X coordinate is 3 and Y coordinate is 2. And say I have another vector here. Okay. That is say 6 minus 3. So what is 6 minus 3? 6 minus 3 means its X coordinate is 6 and Y coordinate is minus 3. Now what I told you is that I have to place the tail of one vector to the head of another vector. So that is what I will do here. So I will move it like this. It will be something like this. Okay. So this has moved here. Now what should be the total length? The total length will be, I will join these two. I will join these two. So this is the total length. And what you can see is that I simply have to add the values because this was 3. Now from 3, I again moved 6. So it will be 3 plus 6 in the X value. And Y value is what? Earlier it was 2 here. But from 2, I moved down to -3. So it will be -1. So that is what we are doing. We are just adding your x values of both and you are adding the y values of both. So that is the way in which your vector addition is done. Now say if you have 3 vectors. So I have another vector u. You just repeat the step. You have 2 vectors. And now this is your final vector. This is v plus w is your final vector here. Now to this v plus w, this final vector, I will add my next vector u. And I will again combine this. So that is the way in which your vector addition is done. So it is performed simply by adding the corresponding components of the vector. So if I have a vector of components v1 to vn, it is belonging to r to the power n because this is an n-dimensional space. And we have another vector w. So v plus w is we are just adding the components. You are adding the first component, you are adding the second component, you are doing that, you are going to the nth component. So this is the way in which your vector addition is done. The next thing what we will do is that we understood what is the addition. Subtraction is also same way. Now we will see how the vectors are multiplied. So is there any way you can multiply the vectors? So there are different ways you can actually multiply them. One of them is your scalar product. It is also known as your dot product. It is also known as the inner product. So there are different ways in which people tell this term, but they are all similar. Whether it is scalar, dot, inner, they all represent the same thing. So what is exactly dot product is doing? It is trying to find how similar are the two vectors. Okay. So if I have vector 1 and vector 2, then I have to find how similar they are with each other. And this is actually given by the dot product of the vectors. So you just do the dot product of the vector. It will give you a number. And that number will tell you whether those two vectors are similar or those two vectors are different from each other. Okay. So let's see what it is, how it is done. So if you have a vector v, which is v1 to vn, and you have a vector w, which is w1 to wn. Now, if you compute the dot product, what it is, you are just multiplying each of the components. So v1 will be multiplied with w1, v2 will be multiplied with w2, vn will be multiplied with wn. So all these you can see, v1 is with w2, v1 is w1, v2 is with w2, vn is with wn, and then you add everything. So when you will be adding everything, you will be getting a simple number. So this will result in a simple number. So number say x, say a. And this number will actually let you know how similar the vectors are with each other. So this we will see now. So how exactly is that defined? So if the number which you are getting, if it is a positive number, that means the vectors are similar with each other. If it is negative, then it will say that the vectors are opposite to each other. And if the value you are getting is 0, then the vectors, they are actually perpendicular to each other. So you might be like thinking how exactly. What happens is that this dot product actually tries to find the angle between the vectors. So when I'm saying dot product, if you are doing with this simple formula v1 w1, if you do either by this or if you do by this simple equation, you will be getting the same result. So what exactly it is trying to say is that you compute the dot product between these vectors, and then you see that if the theta, it is depending on theta, that is the angle between them. So if the angle between the two vectors are like 0, so that means w and v will be in the same direction. This is v and this is w. So they are both in the same direction. So they are more aligned with each other. So it will be a positive value. Now, if the vectors, they are like perpendicular to each other. So the theta is 90 degree. So that is will be a cosine of 90 degree. That means you will be getting 0. That means your final dot product will be 0. So whenever I am getting a result dot product of two vectors 0, that means they are perpendicular to each other. Now, if the vectors are pointing in opposite directions, let's say this is now in this way. So what it tells me that this vector and this vector, the angle is 180 degrees. So cosine of 180 is -1. So you will be getting some negative value. So that is pointing in your opposite direction. So that is what your dot product does. It tells you the similarity between two vectors. And this is actually used a lot when in the future we will be doing in natural language processing, like how two documents are related to each other. So whenever you are doing like whether two images, they are similar image or not. So the image you write in a vector representation, both of the images, and then you compute the dot product. If the dot product is coming to be a positive number, you will say, yes, these two images are related to each other. If the dot product is coming, say some negative number, you will say, no, they are actually pointing in the opposite directions. So this is the way in which, simple way I can say, in which your different recommendation systems are designed. Okay. So here you can see, again, I will say here, the definition is V dot W, that is your magnitude of V, magnitude of W, that is what? The vector, you are adding all the components. So these are like some simple mathematical formula, which if you see 1 or 2 times, you will it will be clear to you. And then you're multiplying by cosine theta. This, if I want to say how exactly this relation came into being, this is what is done, you see. What they do is that you have these two vectors, V and W. I want to see how much is the projection of one vector onto the other. That means if I have two things, say two ways are going, so I want to see like how similar is one thing with the other thing. So that means you have to project it onto this vector. That means whether they are in the same direction or not. If I project it, it will let me know whether V is in the same direction of W or V is in the opposite direction of W. How exactly these two are related. So this projection, this is 90 degree. So you can clearly get from here, if this is 90 degree, then the component of V in this direction will be V cosine theta. So this is our school trigonometry, and this is, you know, V sine theta. So this we all know. So this is your V cosine theta. Now, if I want to see how much is it pointing in this direction of W, I only need to know the direction of W. I don't need to know how long is W, because the direction is mainly I am interested in, whether they are in the same direction or whether they are in the opposite direction. That is what I am interested in. So what people do is that I don't care about the magnitude. I only care about the direction. So this in turn gives rise to your unit vector. Unit vector is vector whose value is 1, whose magnitude is 1. So what it does is that it will preserve the direction here, but the magnitude, it will go to 1. So unit vector is defined as W divided by mod of W. Mod of W, you know, we have defined here, root of W1 square plus W2 square plus W3 square. So that is what we will do. So once you have defined the unit vector here, so what will happen is that my unit vector is defined. I have to find this value. So I will see what is the projection of V on my unit vector. So what is that? That is V cosine theta, because we have understood that here the projection is V cosine theta into the magnitude of unit vector. So what is my magnitude of unit vector? That is 1. So this is how we are getting V dot W hat equal to V cosine theta. Now, if you plug in that relation here, so we can get our relation which we saw here, V dot W is VW cosine theta. Okay. So this is how this relation of dot product is defined. It is nothing but it is telling you, given two vectors, you have to find how much one vector is projecting onto the another vector, or how much one vector is pointing in the direction of the another vector. In order to do that, we only care about the direction. So we introduce something which is known as unit vector. Unit vector is a vector which only takes into account the direction, because its magnitude is 1. Okay. And then we did our simple calculations and we came to this dot product relation. Okay. So that is the way in which our dot product is done. There are other products also, but dot product is something which we will be using a lot when we will be dealing with machine learning in the future. We will be using this dot product a lot there. But there are other products which are used in, say, physics. If you're working in physics or you're working in some other field, they are known as your outer product. So what is outer product? Outer product is you are taking two vectors and you are computing all the, like, you are computing all the multiplications between all the elements. So here I have 4 elements. Here also have 4 elements. So I'm multiplying all element with everyone. So what happens is that here on taking this product, you get a matrix. So let's say if it is of size M and this is of size N, the final matrix will be of size M cross N. So this is another way in which you can actually multiply the vector. In the dot product, what happened? When you were multiplying, you were getting a scalar. Okay, remember, in your dot product on multiply, vectors are related to each other, whether they are in the same direction, opposite direction. Here, what happens in the outer product, we are trying, when we are multiplying the vectors, we are getting a matrix here. Here, what it does is that it tries to find, if I will say what exactly is this used for, this is used to compare the relation between all the components. So you have the relation between all the components here, like V1, W1, V1, W2, all the components relation is there. Now, if you want to do some calculations based on that, you can do it. So this is the outer product. The other product which we use is a cross product. So this is also used a lot. So what is cross product? Cross product is nothing, but here what you are doing, you are multiplying two vectors and you are getting a third vector. First, you got a scalar. In the second product, you are getting a matrix. In the cross product, you are multiplying two vectors and you are getting another vector. So what you see, the relation is V cross W. So V is a vector and it only works in a three-dimensional space. So that is something you have to understand. This product, what it does is that if you have two vectors, you perform the cross product, you will find a vector which is perpendicular to that. So you can see here I have two vectors V and W, okay? So this is my V vector and this is my W. When I'm computing a cross product, it gives rise to a vector V cross W, which is perpendicular to this thing. Okay, so that is why it takes place in three-dimensional space, because three-dimensional space is like this. Okay, so you have X, Y, and you have Z. So if I have two vectors which are pointing like this, the third vector will be perpendicular to that. So that is the way in which your cross product does. It results in a three-dimensional space, a vector that is perpendicular to both vectors. It can only happen in three-dimensional space. We cannot do it in two-dimensional space or in higher space. So here it only works on R3. Okay. So on R3, we do this. So you can see the simple relation is vector n hat. It means it gives the direction of that final vector. The vector which is there, it is the direction. And the direction you can find with the right hand rule. Like if your right hand, so if this is my V vector, as you can see, this is down and I am going in the direction of W. So my thumb is in the upper direction. So that means my final vector will be in the upper direction. That is why the n hat you can see is in the upper direction. If I would have written W cross V, so what would happen is that from W to V, I have to come like this. So my vector will be in the down direction. So my n hat would have been in the down direction. So you can see V cross W is minus of W cross V. So that is what it is given you. Okay. So that is your cross product. So this is the way in which your different products are done. You can do dot product depending on if you want a scalar and you want to find the relationship. You can do your cross product. Okay, cross product is if you want to find a space which is perpendicular to your, if your two vectors, you want to find a vector which is perpendicular to them, then you can do a cross product which will actually result in the of your problem. You have to go with the respective product of that. Okay, so this is the way in which different operations, vector operations are done. Okay, so any questions, anyone? Okay, this we will be letting you know. Okay, Shivani, we will be letting you know of this with the PDF. Yes, dot product I will say here. So vector is basically either a column or a row matrix. Yes, or you can say that you can go in the other way. You can say that matrix is a combination of row and column vectors. Okay, so that is the better way of saying, because we always say that 1 plus 1 makes 2. We never say that 2 equal to 1 plus 1. Okay, so that's we can say in this way that we have vectors and then we can combine those vectors and then we can result in the form of a matrix. Okay, so that is what we do. Dot product. Okay, lot of questions. So let's do one by one. So why cross product is 3D? What leads it to be 3D? Okay. So by definition, what happens is that the way cross product is defined, it says that it results in a vector which is perpendicular to the two vectors which I am giving. Now say if you are in a two-dimensional space, okay? Let's say if I have only x and y coordinate. So if I am defining here two vectors, I cannot go any perpendicular because this is a plane. I am only restricted to the plane. Okay, so I cannot go above the plane. So that is why in two-dimensional, you cannot do that. In three-dimensional, what happens is that you have x and y. So you have this xy, you can go perpendicular to that. That is why it is known as your, there in three-dimensional, you can do that. Now, if I go to four-dimension, you see there at that case, if you have two vectors, if you want to go perpendicular, you don't have only one dimension. You have two more dimensions there because total you have 4. So you cannot have a single vector now. Now you have to go to some concept of plane and different thing. That is the reason by definition, cross product restricts itself to 3 dimension. Okay. And what is the difference between dot and cross product? Dot product is used to find the similarity between the vectors. Okay. Dot product, it results in a scalar. When you are doing a dot product, you get a number as a result. So that is telling you how the vectors are similar to each other. When you are doing a cross product of two vectors, you are getting another vector which is perpendicular to that vector. And cross product only works with a three-dimensional vectors. Dot product, it can work with any dimensional. Okay. Now the thing is, one of you asked, how is cross product used in machine learning? So, you know, cross product is actually used in computer vision a lot. So when we will go to computer vision, then you will see that there are people, in order to do some 3D reconstruction, they do this. Okay. The result of the cross product is telling you that this is the vector which is perpendicular to the two vectors of whom you have done the cross product. So x and y, you have done a cross product, it will give a vector z which will be perpendicular to x and y. Okay. And when to use outer product and cross product, as I told you, depending on your operations. If you want to get a final result as a vector, perpendicular vector, you go with cross product. If you want to get the final result as a matrix, you go with the outer product. Okay. Cross product and outer product are different. You see, cross product you are defining as VW sine theta. Outer product, what you are doing? Outer product you are doing as this. You are multiplying each component with each one. Okay. So that is your outer product. Outer product is not used that much in machine learning. Since this is there, that's why I just showed you. People mostly use dot product. Dot product is the one which we use a lot in the machine learning algorithm. And cross product is used when you are dealing with 3D computer vision techniques. Okay. Last line, which is written in brackets. Okay. Okay. Sure. So this is actually the formula how the cross product is done. Okay. So how it is done is actually, so you see cross product. So I have said this is in R3. So what I define is that in R3, I define 3 vectors. So it is like x vector, like in the x-axis, you have y-axis, you have z-axis. Okay. Now what I do, what is the component of V in X, Y, Z? So it is V1, V2, V3. What is the component of W in X, Y, Z? It is W1, W2, W3. Now when you are doing a cross product, V cross B, so what is happening? What is the X component of this final vector which you are getting? So I told you it is a perpendicular vector. So what is the component of that vector? The X component of that vector will be, so let me give a different pen. Yeah, the X component of the vector will be, you have to multiply this with this. And then, so it will be V2 W3, I am multiplying this, minus W2 V3. So you see that is what it is given. V2 W3 minus W2 V3. Okay. Now the Y component. So how we go to the Y component? So Y component will be, I will take the X value and the Z value. So it will be V1 W3 and W1 V3. W1 V3. So this is how it is done. So you see here, V1 W3 and W1 V3. Then similarly for the Z component. So here I will take X and Y only. So you see V1 W2 minus V2 W1. So this is the final vector which is formed. This is perpendicular to W and V. What are the components of these vectors? That is what I have written here. Okay. So this is how your cross product is done. So now that we understand these different type of products, so let's now move to the second part. So we still have a little more to cover. So let's go there. So let's come back to this equation now. So this equation, we saw that it is XA equal to Y. Now we understand the vectors. So what are the vectors? Vectors are the values. So these are the values in your feature space. So like Y1, Y2, Y3. So these are like some numbers which are written in the form of a column. Okay. Now the thing is that we can I can ask you the question, what should be the nature of A and Y? Like what values should I take for A and Y? Here, there should be some restrictions. No, A cannot be like some complex number, or A cannot be like this. So there can be some restrictions here. So we have to understand what should actually be the nature of these vectors. In order to do this, we will understand the concept of vector space. Okay. So the next thing what we'll try to understand is what exactly is our vector space. So what is vector space? Vector space, as you know about group theory. So like in group theory, you know, there are certain axioms which you have to satisfy in order to be a group. Similarly, a vector space says that there are some rules which you have to satisfy in order to say that it is a vector space. So what it says is that if you have some vectors, say V. So in our case, what are those? A and Y. Okay, so A and Y are in our case the vectors. So if you have some vectors V and you have some scalars, okay, so we can have some scalars. Now, if these vectors and these scalars, they satisfy these conditions, then we can say that they form a vector space. So let us try to understand this with an example. Okay, so I will be skipping this. I will be giving you an example, then I will come back. So what are the conditions it has to satisfy? So let's say if you have two vectors, okay, I have vector U. So say I have vector, say U, I have vector V and I have vector W. And I'm saying that they all belong to my vector space. My vector space is R3. What is R3? That all these vectors are three-dimensional real numbers. Okay. So U is a vector which is three-dimensional real number. Say I define it, let's say with some values, say 1, 2, 3. Okay. So U has this component. So this is the XYZ component. Then V also I'm defining, say 4, 5, 6. You can give any arbitrary real numbers. You don't have to take these only. You can give any arbitrary real numbers. W, say I'm saying, say minus 1, 2, 4. Okay. So this is like I have defined three vectors and they are belonging to R3 space. So in order to say that R3 is a vector space, what we have to see? We have to see that it satisfies these conditions. First condition is, if you add first u and v, so you know how to do vector addition. You add first u and v. The result what you are getting, you add that to w. Whatever result you will be getting, it will be same if you add first v and w and then you add u. So this is known as your associativity conditions. So this is something which should be satisfied. Then the vector space R3, it should have a zero vector. That means the origin. So if you define this thing, this is your XYZ, then that is the origin. So it should have a zero vector such that if I add this to any vector, it will give me back the same vector, because 1, 2, 3 plus, if I add to it the zero vector, that is 0, 0, 0. So you will be getting the same result. So that is what you need to have a zero vector. Then the third is, you need to have some negatives. What is the negative? It says that for every vector belonging to this vector space, there should be a negative vector. That means if I have a vector 1, 2, 3, I should also have a vector -1, -2, -3. Such that when I'm adding both of them, I'm getting the result 0. So you should have a negative number, because you can easily see, if I have a vector 1, 2, 3, which is defined like this, then obviously in this space somewhere I will have a vector -1, -2, -3, which everything will be in the negative space. So this is something which has to be defined. After that, if you multiply the vector by any scalar, it should be in that space only. That means if I have a vector, say 1, 2, 3. Okay. So I have vector 1, 2, 3. If I'm multiplying with a scalar, say if first I am multiplying with 2. So what will happen? It will become 2, 4, 6. So 2, 4, 6 will also be there in this space, because we know in this three-dimensional space, it will 2, 4, 6, you can easily represent. And then if you multiply it with say 100, so it will be say 200, 400, 600. That also you can represent in this space. So it will be always in this R3 space. You cannot go to R4 space. Like if I multiply 1, 2, 3 with 2, I cannot get the number like 2, 4, 6, and say another number 5. I cannot get this. I cannot go to R4 space, or I cannot get like only 2 and 4. I will always get 3 components only. So that is why R3 is your vector space. Similarly, you can have this property, like if you add two numbers and then you multiply with the vector, it will be same as if you are adding them separately, multiplying them separately and then adding. So this is what we can say. So these are the different conditions which needs to be satisfied in a vector space in order to be represented as a vector space. So what are the different vector space? I have like R3 as a vector space. R2 is another vector space, because if I say R2, it means all the numbers will be two-dimensional. So I will have say 3 and 4. So with 3 and 4, I have say another vector, it will be say 10 and 20. So these all vectors are represented in R2 space. And if I perform all these operations, which you can today check after the class, you start performing all these operations, you will see that all these conditions are satisfied. That is the reason why R2 and R3 are your vector spaces. Okay. Now let's see an example. So let's consider we have a three-dimensional Euclidean space, which is denoted as R3. Okay. So this consists of all triplets of real numbers x, y, z. X, y, z are real. So I have shown you how with vector addition, you are satisfying the property. With scalar multiplication, you are satisfying the property. If you add it with 0, you are getting this same vector. If you're adding with the inverse, you're getting the 0 vector. So R3 is your space. Now, let me ask you a question. What happens if I remove this 0 from this vector space? So what will happen to R3? Will R3 be still a vector space, or it won't be a vector space? Anyone? So let me check the chat. It won't be. Good. Yes, good. It won't be a vector space because you can clearly see here, because what happens is that if I remove that, we will get a subset of R3 where this scalar multiplication won't hold, because now if I multiply 0 with any vector, I will be getting 0, 0, 0, and we see that 0, 0, 0 is not there in R3 anymore. So we are saying that our vector space won't be a vector space anymore. Then the next question comes, can you find any subset of R3 which will still satisfy all these conditions? Means R3 is the whole vector space. Now within this whole vector space, can I find a smaller space where all these conditions will still be satisfied? So that is known as your subspace. Okay. So subspace is that it is a non-empty subset of vector space where all your requirements of the vector space is satisfied. Okay. So we'll see this with an example. By say your original vector is R2. Okay, I'm giving you a very simple definition, R2. Now what happens is that 0 by default is always a subspace, because 0 plus 0 is 0, 0 into something is 0, 0 minus 0 is 0. So 0 by default, it is a subspace. You go to any vector space, Rn, R to the power 5, R6, 0 will be by default a subspace. Now let's consider a vector V. Okay. So here what I am saying, that I consider a subspace where I have only two vectors, 0 and V. Okay. So now I ask the question, is Vs now a subspace? Like, can I say that Vs by definition, it is a subspace? Will it be satisfying all the conditions? That is something we have to understand. So what happens is that V by itself, it won't be a subspace. But if we start taking all multiples of V starting from the origin, it will give you a subspace of V. Why? You can see here is that I have V. Okay, so I have, let's say, this vector V. Now, if I take all the multiples of V, say 2V, so this is like I'm multiplying it with 3, I'm multiplying it 4. So what will happen is that in this space where you have 0, then V, then 2V, you go to infinite, 3V, 4V. So what will happen is that if you add this, you will be getting another vector which will be remaining in this set. If you 0 is there, so no problem. There will be a negative also, minus V, minus 2V, because I am doing all the multiples here. So the negative vector is also present here. And if you multiply with any scalar, you will be again going back here. So the thing is that if there is any vector which is passing through the origin, then all its multiples will actually result in the subspace of V. So that is something which we need to understand, that for every vector space, there is a subspace which are like multiples of V which satisfies these conditions. Okay. Now, if I go to say 3 dimension, so after I do this, I will be coming back to your questions. So let's say if I am going to 3D space. So what is the possible subspace? Anyone? What is the possible subspace of R3? By default, what is the subspace of any vector space? What is that? 0, 0. Good. So by default, my first subspace will be the origin. So this is the first subspace. The next subspace will be a line, because as we saw in R2, if I take the multiples of line, it will be remaining in this space. So anywhere I go, I will stay in this one dimension only. Okay. So this is your another subspace. Since this is R3, there will be another subspace. That will be your plane, which is passing through the origin. That means now this is on 2 dimension. Since in R2 what was happening, we can only go in 1 dimension, because you have 2 dimension, you can draw a line only and nowhere you can go. Now when you are coming to 3 dimension, you can actually start thinking of a plane. So if means we have now 2 vectors. So say I have 2 vectors and these 2 vectors are forming a plane. And if I elongate these two vectors in any direction, they will actually give rise to a plane. So these vectors I am increasing in both directions. So you see I am getting a plane here. So that is okay. So what if you take some other vectors other than multiples of V? What happens is that I am saying that in order to be a subspace, it has to satisfy all the conditions of the vector space, which I told you. Now, if I take, say, V, then if I take, say, some other vector, let us read. So I am taking some vector v1. So this is a normal thing. This is like you are saying, I am taking vector v1 and I am taking vector v2. That is a normal condition. I am saying that by taking one vector in R2, can you define that that is a subspace or not? Because by default R3, it says that any vectors which are there, it will be satisfying all the conditions. But our question is that by taking one vector, can you say that with this one vector, you can construct a subspace? Okay. So that is, if I take one vector, then I have to go with multiples of that vector only. Because if I don't go with multiples of that vector, by adding v with some other vector, I will be getting again another vector. That will give you the problem. You won't be then in that space. If I take v with 2v, I will be getting 3v. And 3v is there in my vector space. Okay. Akshay, is it clear? Say if you are saying v1 and v2, I am making a vector space. So if you are getting v1 and v2, if you are adding, you are getting v3. v3 is not there in that space. But if I am taking multiples of v, v2v, 3v, 4v, if I am adding v plus 2v, I am getting 3v. 3v is in my space. So that is the reason we are saying that is your subspace. Okay. So vector space is the whole R3 space. R3 space can have subspaces. Subspaces are the vectors which will be forming those things. So the thing is R3. Yes, by default, R3 can have subspaces R2, R1. By default, it can have. But I am saying that can you construct some vectors for me? So when I'm saying that is R1, so you can see here what I did here was first I defined this thing. So this is your R0. Now I said this line can form a subspace. So this is your R1 because you are staying in one dimension only. You are elongating there. Now I will say R3 can also have two vectors. So this is vector, say v1 and v2. And these two vectors, I will be taking the multiples of them. All the multiples of v1, all the multiples of v2. And what they will do, they will span a plane. So this will take into account a plane. So if you do in 3 dimension, if two vectors, if you are stretching, you will see it will form a plane. So that is your R2 space. So yes, by default, R3 is having subspaces R2 and R1. That is in the form of a line and in the form of a plane. Okay. So these are like different planes it can have. Then comes the question. So this is what I want you all to understand now. Say if I have a vector v that is belong and I am multiplying it with a scalar. Okay. So what is the subspace it is forming? I'm just multiplying with a number. I have a vector line in R3. So let's say I have this vector R3. This is a line. I'm multiplying this with a number. So what is the subspace I'm getting here? Yes, anyone? What is the subspace I'm getting here? Yes, line R1. Good. So you have a vector. So this is the thing which I'm showing you. So you see you have a vector here and you are multiplying it with a number. So what is happening? You are only staying in a line. So you are getting a line here. Okay, so the subspace here is the line. Now let's say if you have a vector V and W, and they are belonging to R3. So in the space R3, you have two vectors. You are getting a plane R2. Good amount. So you can see you are getting a 2D plane here. You are getting a R2 here. Now, if I have a vector, let's see here. U, V, and W. I have three vectors and I am taking all the possible linear combinations. So what is happening? I am in a 3D space and I am taking all the linear combinations. Yes, good. I am getting R3. Sorry. Good. So I can see you can understand the concept now. So I'm getting whole of R3 now. Similarly, you can go like this. So now if I am in a 4D space, so this is now in a 4D space. And here I am getting three vectors. So in a 4D space, I am taking three vectors. So what is the subspace here of R4? R3. Good. So you are getting a 3D hyperplane. So that is your R3. So the other way people say is hyperplane because it means in a 4-dimensional space, you are getting a 3-dimensional plane. That is your R3 plane. So now that you are clear with this, let us go to our final question. So final question here is, I have this R4, I have these 4 vectors, and I am writing it as AU plus BVWC. So what is the subspace here? I have 4 vectors in, yes, see it carefully. I have 4 vectors in R4 plane and I'm taking the linear combination of these 4 vectors. Yes, R4. By definition, you will say it is R4. No, students, you are, see, I have now 4 vectors, U, V, W, X, and if I just look at it, AU plus BV plus CW plus DX. So I'm taking all the 4 vectors in the 4 plane. So possibly I'm spanning over the whole space. But there is a little bit trick here. So that is what I want to say here before we go next. So I see I have 10 more minutes. Okay. So what you can see here is that by definition, you will see, but you see there has been a bit change here. So what is the change? You can see the vectors U and W. Okay. So the U and W, you can see they are related to each other. They are actually multiples of each other. If you multiply U with -1, it will give rise to W. And if you multiply with 2, it will give rise to X. So if I modify this, it is actually coming to these 2 combinations, U and V. Now you can tell me what is the space here. So I'm getting R2. Great, great. So here what we saw is that just by saying that I have an n-dimensional space, in that n-dimensional space, I have given you n vectors and you have to tell me whether those vectors, they are forming the subspace or not. You cannot simply count and tell me that. You have to see whether the vectors are multiples of each other or not. So that is something which you have to check. And this in turn, it gives rise to something known as your independent vectors. Okay. So independent vectors is something which you will see a lot in the future, which says that these are the vectors within a vector space that don't have any relationships among them. Okay. In other words, if I say that I have some relationship between 2 vectors, let's say it will be like I have 2 vectors X and Y. I will say that there is a relationship like 2X equal to Y. So what this in other way, it says that I can relate X and Y as 0 equal to 0, where I have some coefficients, that is C1 is 2 and C2 is -1. Okay, so it is saying that C1X plus C2Y equal to 0. You are getting a combination like this where C1 and C2 is this. So this is what it is saying, that if you have a set of vectors in Rn and you find this relation here, that C1 plus B1, C2 plus V2, if all the coefficients are 0, then you will say that vectors are independent vectors. But if the coefficient is not 0, as you saw in this example, the coefficient is not 0. That means these vectors x and y are related to each other. If the coefficients are all 0, we can say that the vectors are independent of each other. Okay, so that is known as your independent vector. So why is this important? This is important because as you saw in our equations, when I told you xa equal to y, as you saw xa equal to y, so what is something we have to see? We have to see whether all these values, they are independent of each other or not, because this is basically you're solving these equations like say 5x, say I will solve like 5x plus 3y. So this is say the age of the house plus the area of the house. I'm taking with the age and area, I'm getting some result like the price of the house is say 120. Now, if I have another value in my data, is the age of the house. And this is the area of the house with something like this. Okay. And this I'm getting as 240. Now you can see that these two, if you write it in a vector notation, so it what will it will be? So if I write it in my equation, so it will be 5, 3, 10, 6. Then it will be xy equal to this. So you can see these two equations are actually same. If I multiply this by 2, I am getting this same equation. So if both the equations are the same, there is no way you can solve these equations, because ultimately I'm getting only one equation. From there I have to solve x and y. That is the reason why we have to check for the independent vectors. In the data, the vectors, they should be independent of each other. Okay, otherwise it won't be resulting in giving you a solution to that. Now, yes, independent vectors, is it clear? Or one dimensional is scalar. One dimensional means a number, that's all. Rohan, is independent vectors clear to you? Yes, no, can you please reply? And you, everyone, independent vectors, is it clear to you all? Okay, great. Okay, great. So again, I will quickly, if I want to say, independent vectors means the vectors which don't have any relation among them. That's why if I am saying here, as you can see here in this previous thing, if there is a relationship between the vectors, okay? So what happens is that you see x and y, if they're related, then it happens like 2x minus y equal to 0. So if I take this form C1, V1, C2, V2, so I can see that C1 and C2 are 2 and minus 1. So that clearly says that there is some sort of relation between x and y. If there is no relation between them, then what happens is that all the coefficients will be 0. All your CIs will be 0. And why exactly this is important? This is important because when you are solving your linear equations, if both your linear equations are related to each other, because you know, in order to solve two unknowns, you need to have two equations. Okay, but here I have two equations, but these two equations, you can see one is double of the other, so we cannot get our result here. So that is why we need, this is one of the most important concept here. So now, what are the basic linearly independent vectors? So when we were telling our vector space, So when we are saying, no, in our vector space, we have the different vectors. So we can say that when we are defining in our vector space, are there any vectors which are linearly independent of each other? So let's say I have a vector space R2. Okay, so in R2 we saw we can define different vectors, we can define a line, we can do all the things. But in R2, are there any vectors which are like they are linearly independent of each other? Like you cannot find any relation between these two vectors, and you can construct any vector from this vector. That means I give you a vector and I can say with this you can construct any vector of R2. So if you can do that, that is known as the basis of that space. So you can see here, let's say basis of R2 is 1001. Okay. So what is 1001? It spans R2. Why? You see, 10 and 01, you cannot find whether they are related to each other. There is no way you can find the relation between 10 and 01. You cannot go from 10 to 01. Okay. So that is something that it says that if I take C1 of 10 plus C2 of 01, you won't find any relation you can construct with this, because you say, if I say in R2 I have a vector, say 7, 8. I can easily construct 7, 8 from this, because 7 into 10 plus 8 into 01 will result you in 7, 8. This will give you 7, 8. Okay. So these are your basis vectors. That one. So in other words, they say that these are the vectors. They don't have any relation among them, but using these vectors, you can construct any vectors in your vector space. So this is of R2, you have 1001. Similarly, in R3, you have this x-axis, y-axis, and the z-axis in simple way. So any vector you can write as a multiple of x plus multiple of y-axis plus multiple of z-axis. Any vector in 2 dimension, you can write as a multiple of x plus multiple of y. So this is the concept of your basis vectors. Is it clear? Yes. So when you are saying that basis vectors don't intersect, so basis vectors you can simply say that they don't have any relation, or otherwise intersect. I don't know whether you can say that. Intersect is not a right word. You can say that they don't have any relation among them, and using those basis vectors, you can construct your inter-vector space. So any vector in R2 you can write as a combination of these basis vectors. Any vector in R3 you can write as a combination of these basis vectors. So these are the conditions it should have: linear independent, and any vector can be constructed through this thing. Now the question comes, are these the only basis of R2, or there can be any other basis vectors? There can be, and that is your homework. So just think about this. In R2, apart from 1001, can I construct any other vectors which will be independent, linearly independent, and using those vectors you can construct any other vector? So that is what you need to know, that in any vector space you can have multiple bases. So these are the these are the like simple bases, we can say. And another thing you should know, that in a basis, the number of vectors should be equal to the dimension of the vector space. So if I have R3, I have 3 basis vectors with 3 dimensions. If I have R2, I have 2 basis vectors with 2 dimensions. So that is some conditions you have to satisfy. And with that, you can construct any number of basis vectors. So these are the things you can do, and as an exercise in order to improve it. Okay. So you can see here that these are the things which you can check, whether 1, 1, 2, 3 forms the basis of R2, or whether these 3, it forms the basis of R3. Just check whether these vectors are independent of each other, or if you can construct any other vector as a combination of these vectors. Okay. Now that we understand these basis vectors, let's now go to our matrix. So 3 more slides and then we'll be done. So what is a matrix? Now we know about vectors. We can say that matrix is nothing but this is a collection of row vectors and collection of column vectors. So you are collecting now the vectors and then you are saying I am forming a grid-like structure, and this grid-like structure is actually containing all the information here. So that is your matrix. Now, if your grid-like structure, the number of rows and columns are equal, that will be your square matrix. And if your rows and columns are not equal, then that will be your rectangular matrix. Okay. So square matrix is something which people, they work a lot because that is simple. Rows and columns are equal. Have something rectangular matrix also, there are certain ways you can work, but that is something you need to go into very much details of it. So I will just give you some basic characteristic of the matrix. So if you have a square matrix, you can actually compute the trace. Trace is just, you will be adding along the diagonal. So I have the diagonal elements here. So I will just add all the diagonal elements. So that will be giving you the trace of a matrix. Just 1 minute, give me a minute. Just 1 minute, okay. Okay. Now that we understand the trace of a matrix, the next thing which we will do is that we have to find the determinant. So determinant of a matrix is nothing but what it does is that it tries to understand like how exactly is the transformation working. As I told you, matrix is nothing but it is a transformation. So I have X, which is acting on a vector A. And it is resulting you. Now the thing is this X is the form of a matrix. Now I can ask you this transformation, whether it is doing a correct transformation or not. That you have to check first. And in order to check that, what we do, this X matrix, you can compute the determinant. The determinant is a simple way. It represents like after you are performing your transformation, whether the vectors, they are doing a good transformation or not. So that is taken care by determinant. How the determinant is done? So if you have a 2-dimensional matrix, you just multiply the adjacent things. So you multiply this and then you subtract with this. So this is the determinant. If you have a 3-dimensional matrix, what you do? You take the first row. So first row x11, then you take the cofactor. Then minus the second one and the corresponding cofactor, that is z values. When you are taking z, you are taking the x and y values. And then you do the calculations. So you will get the result. The result will tell you whether you are doing a good transformation or a bad transformation. Okay. So that is the thing what your determinant of the matrix is telling you. Now that we understand the determinant of the matrix, so these are some properties you need to know. That if a matrix is, if your determinant is a real number, then you can do the transformation. If your determinant is 0, then your transformation cannot be done. And if your matrix is containing some zeros of rows and columns, the determinant will be 0. If your matrix will have 2 similar rows, okay. So you can see here, my matrix here has these similar rows. This is 2, 2, 2. This is 8, 8, 8. So you can see this 2, 2, 2, 2, 2, 2, they are similar. So if I have 2 similar columns or similar rows, the determinant becomes 0. So why I am telling you this? This is because as we come to the last part, it will become clear. That is what I won't be going into this. I will be showing you a simple example. So this example is telling you that as I told you, I have to solve this equation xa equal to y. Now, when I am solving xa equal to y, what happens is that if I have two lines which are similar to each other, as you can see here, I am giving you 2, 3, 4. Then this line is the multiple of this line. So both these lines are similar to each other. So what will happen is that in order to get 3 real values, I have to solve 3 linear equations. But in case I have only 2 equations, so what will happen is that I won't be able to get any solution here. So if I'm doing this problem, I won't be able to get any solution. So this is what your determinant and the rank tells you. Rank will tell you how, so you know how to check for independent vectors. So it will tell you, so since a matrix is formed of independent vectors, it will tell you how many independent vectors are there. If there are any dependent vectors, then the rank will be less and the determinant will be 0. And it will tell you that you cannot get a solution of this equation, that your machine learning algorithm cannot give you a solution here. So that is the reason why we are computing a matrix. We always determine the rank of the matrix. We determine the determinant of the matrix, because rank and determinant, they will tell you whether there are any columns or whether there are any rows which are exact replicas of each other, or whether they are dependent on each other. Okay, so that is the reason why the rank of the matrix is very important, or the determinant of the matrix is very important. So these are something you can see here, that the rank by definition, it should be the number of rows or columns of a matrix. But if the matrix is not of full rank, if there are any dependency, the determinant will be 0, and it will tell you that there's this probably next class I will tell you. Now let's come to the final slide. We had this equation xa equal to y. Now we have to solve this equation. How we can solve this? We need to find a which is unknown. So what we do is that we just do this simple transformation. That is, we multiply both sides with x inverse, that is a matrix inverse, into y. Now we know what is the inverse of a matrix. That is the determinant of the matrix. You have to divide it by the determinant of the matrix with the adjoint of x. Now this is where it is important. As you can see, if the determinant is 0, you will never find any solution for A. But if the determinant is not 0, it will tell you that the system of equation is consistent and you will be able to find a unique solution. So that is what we need to understand. So this is what I have been trying to tell you, that every equations in machine learning, it boils down to simple, this type of linear equations. But you have to first understand whether this system of linear equations can be solvable or not. In order to do that, you have to understand the concept of the determinant of the matrix. You have to understand the concept of the rank of the matrix. You have to understand whether the vectors which determine the matrix, they are linearly independent or dependent on each other. So once those pictures are clearer to you, you will be able to find, okay, so now this system of equations I can solve, they are consistent and they can actually give me a unique solution. Okay. Any questions, anyone? Sorry, I had to rush a bit in the last part because it was already past 9. Yes. Any questions? Basis vector similar to subnetting in networking. No. These are different things. And basis vectors is different. Okay, subspace concept. Sure. I will tell you subspace. So vector space, vector space, as I told you, that vector space is something which is like R3 space where you are satisfying some conditions, which I have defined the conditions. Now the thing is that is the whole space. Now I am asking whether within that whole space there is some space which also satisfies all those conditions. Okay, so this is like a group and subgroup. You might have seen set and subset. So that we have a bigger group, but within that, do we have a smaller space where all these conditions are satisfied? Let's say 0. We know 0, if we add to 0, we will get 0. 0, if we multiply with 0, we will get 0. So 0 by default, it is a subspace of every vector space. Okay. Then if you have a single vector, now if you take multiples of that vector, what will happen is that vector, if you add with the multiple of that vector, you will get another, like if you have vector v, you take multiple of v, that you multiply it with 2. Now if you add v plus 2v, you will get 3v, which is also a multiple of v. So you will always be remaining in that line only. You won't be able to divert from that line. So that is also a subspace. Subspace means within the whole space, you have a region where you are satisfying all the conditions you require for a vector space. Okay. Any other questions? Okay, rank, sure. So rank, yes, sure, I will tell you. Rank is what happens is that, so let's go back here. So rank is telling you, as I told you, matrix is a combination of rows and columns. Okay. Now what happens is that when I am saying that it is a combination of row vectors and column vectors, we have to check whether those row vectors and column vectors are independent of each other. Now, if those row vectors and column vectors are independent of each other, then the rank of the matrix will be the number of rows or the number of columns, whichever is lesser in our case. Okay. But if they are not, if they are dependent of each other, then your rank of the matrix will be some smaller number, because your number of independent rows and columns will be less. So this in turn, what it will do is that it will tell you that there are some vectors which are dependent on each other, and this in turn will tell you that the determinant of the matrix is 0, which in turn will tell you that no solution exists for these equations. We have to look into those equations. Okay, that is why the rank of the matrix is important. It tells you how many independent rows and column vectors are there, whether there is any vector which is dependent on the other. If there is, then the rank is very less than 0. As you can see in this example, you see the number of rows and columns is 3. But if you add these two rows, 1 plus 0 is 1, 2 is 4, 3 is 5. So you can see the rank of the matrix is 2, because only 2 vectors are independent. The third can be obtained by adding these 2 vectors. Now you see here the rank will be 3, because all these 3 vectors are independent of each other. We cannot obtain another vector by adding or subtracting or multiplying any other vector. So that is the reason why rank of a matrix is very important. Is it clear, Devans? Yes, this PPT, it will be shared afterwards. We'll see. Okay. So what we covered in today's class was summarizing. Today we understood some basic concepts of linear algebra. We saw how in the context of machine learning, linear algebra is really useful, because we solve some basic linear equations. And these linear equations are nothing but they are the transformation of a matrix. So matrix is applied as a transformation to a vector, which is transformed into another vector. Okay. So x applied on A will give you another vector. Now this simple equation solving, it actually helps us to understand the concept of vector, the concept of matrices, the concept of vector space, because unless and until these concepts are clearer to us, we cannot, understand a consistent solution on. So that is what we tried to understand today. So we understood about the vectors, we understood about the vector operations, we understood about vector space, subspace, linearly independent vectors, we saw matrices, we saw what is the rank of a matrix, we saw what is determinant, and finally we combined everything and we saw how we can find the solution to that. Okay, so I think if any other questions? Any other questions? X, there are three independent vectors. 1 minute, let me just check. But how is it to? Just 1 minute. You see here in this X, you can see the third vector is obtained by adding these two rows. 2 plus 2 is 4, 3 plus 2 is 5. Okay, so only two independent vectors are there. The third vector is obtained as a combination of this vector. So that is why the rank here is 2. Okay. Okay. Any other questions, anyone? So I hope you understood today's session. And if there are any questions or anything, you can post in this chat. I will get back to you, or we can discuss in the next session. Okay.
Okay, ma'am. So thank you so much, ma'am. We'll wind up the session now.
Yes.
Thank you all and good night, everyone. See you all on next Saturday. Okay. Thank you all.
Thank you, everyone. Thank you.